the attendance check for the rest of the semester. I just want you guys to come here in person. Obviously, this is not working out for some of you who attend the courses online. Okay, so we didn't do very good in the midterm CTF. Several of you did very good. I think there were like maybe three people solved all 4 challenges. That's it. Out of 44 students, 3 solved all challenges in the allocated time. Guys, stop. Okay. So when you come here, I expect you to expect me, and I also expect you. Okay. So do not fall here in class. You come here to learn. I come here to show you guys what to learn. Okay. Okay. So now we are moving to the second half of the semester. I hope the first half have been quite interesting. Can you guys hear me? Is this working? A little bit? Okay. So the first half, we spent most of the time talking about stack-based buffer overflow, and that is the basics. So the second half, we're moving to other topics, and we will move a little bit faster. So before the midterm CTF, we talked about the stack cookies and how to bypass them. So today we will talk about other 2 defense techniques. So those defense techniques are not necessarily only for stack-based buffer overflow. It can defeat actually all kinds of attacks, but I discuss them here because they can also defeat buffer overflow somehow. Also, Wednesday this week, we will talk about shellcode development. We'll talk about how you write assembly code to develop some kind of a shellcode to pass some kind of a sanity check. So after that, next week, we move to format string vulnerability, which is a very, very interesting topic. So after that, we move to ROP. Okay, so the first topic we will talk about today is called ASLR, or Address Space Layout Randomization. So this is a technique that is designed to impede exploitation of some vulnerabilities, including buffer overflow. So this technique has been deployed in all our modern operating systems. So a lot of techniques we talked about so far, they have been deployed in our modern operating systems. Your phone is using them, but those IoT devices, very low-end IoT devices, for example, if you have an Amazon Dash, if you have a Google Nest, those devices do not have those techniques yet. We will talk about why. So this technique works by randomizing the addresses of a process so that attacker is unable to know the exact location of the functions, the code they need to know in the attacks. So a little bit of history about this technique. Back in 2001, or 20 years ago, the Linux PAX project, they first coined this term, ASLR. They published their first design and the implementation of ASLR in July that year as a patch for the Linux kernel. The first mainstream operating system to support this feature was OpenBSD version 3.4 back in 2003. Also, Linux started to support this officially, not as a patch, back in 2005 in Linux 2.6. So back then, we were still talking about ASLR for applications, for user-land applications. So what we're going to look at today is also for user-land applications. But now ASLR is also moving to the kernel space. Windows started offering kernel and user space ASLR back in Windows Vista in 2007. Both Android and iOS support userland ASLR in 2011. So that is only 3 years after iPhone, the first ever iPhone came out. Back in 2012, both OS X and iOS started supporting kernel space ASLR. Linux also offers kernel space ASLR starting from 2014, but they are not supported in embedded devices so far, IoT devices, because so far this technique, most of the deployment, they rely on a huge address space. To get a huge address space, you usually need a MMU. So in our class, we have been using 32-bit systems and 64-bit systems. So you can say in 34-bit systems, the address space is small anyway. Even if you are using MMU, this address space is only 4 GB. That's quite small. Means even if you randomize things, the attackers can still guess, do a lot of guess. But if the address space is huge, like 64-bit, it's very, very difficult to guess. For low-end IoT devices, embedded devices, we do not even have MMU. So all of you, when you took operating system class, MMU, memory management is a very important part of that class. But you probably don't know that a lot of devices you are using right now, they do not even have MMU. So everything on those devices are still on a physical address space. And the physical address space usually is small, it's still 4 GB. So next, let's see how the user space ASLR works. So in a stack-based buffer overflow example, especially in the return to libc example, what we do as an attacker is we need to place some shellcode onto the stack, then we jump to that shellcode. Or we find out where is a specific function in that address space, and we jump to that function, right? So in the shellcode case, we can put a lot of NOP sled. One NOP sled is 1 byte in x86. We can put thousands of NOP sled there to increase our chance to jump to that NOP sled. But if we want to jump to a specific function or like a return to libc attack, we have to know where that function is, that exact address of that function, so we can jump to the beginning of that function. So as a defender, if we want to defeat this kind of attack, one option is we randomize that function's address. Every time that function or every time a program is noded to be executed, those functions will have a different address. So every time you have to guess attackers, and we can make that guessing very, very difficult. So that is the idea of address space layout randomization. The high level idea is we randomize things, randomize their locations in the address space. So attacker will not know where to jump to. So this defense can also defeat a more advanced attack, which we will discuss later, the return-oriented programming. In that attack, we need to define the gadgets in the address space. A gadget has a special purpose, and we are going to chain those gadgets together we can build a chain of gadgets so it can do arbitrary computation. But to do that, we need to know the address of gadgets. If we do not know the address of those, we cannot chain them together. So this approach, this defense can also defeat that. However, every defense comes with a cost. And in security, especially for defense, it's always a trade-off between security and cost. That's why all those approaches we are saying, they are not perfect. Even though the idea of address space layout randomization sounds perfect, if we can randomize it, if it's super random, it's very difficult to guess. But however, the entropy may not be enough to make it very useful. And that's what we're going to say today and how we can defeat this kind of defense. Another concept related to ASLR is position independent code, PIE or PIC. Sometimes we call it position independent executables. So PIC or PIE is basically a body of machine code that can execute properly regardless of its absolute location. So So most of the instructions you have been so far, they are PIC already. Doesn't really matter where they are. For example, if there is instruction to add the two registers together, no matter where that is, it will add two registers together. Doesn't really matter. But there are instructions. Their functionality is somehow related to where they are. For example, if that instruction is to load another memory location, but that memory location is a relative location to itself, right? The instruction is to load a byte from another memory location, which is 200 bytes away from it. So that is an instruction. Obviously, this instruction is not location independent. If it works, depending on if you place that at a right location. So if we want to randomize code, we want to put it in at different locations. We have to remove those kind of instructions, change them to equivalent ones, okay? So this old compilers, they were assume a lot of things are fixed. Instructions are at a fixed location, resources, data, they are at fixed location. So to make things faster, we can rely on those information where they are. So those codes do not have to be position independent. But now we care about security. We are changing things more position independent. So things will be a little bit slower, but at the same time, we can randomize it. So if you remember, this is a picture from the first class. And we said this is, in general, the address space of a Linux process I think it's more like a 32-bit, because the address space here is 4 GB. And this is its old address space. Right now it's randomized. So you can see on top, we have 1 GB of kernel. Then we have a stack, which goes down. Then we have some memory mapping segments. Usually there are libraries, like C libraries. We place them in the middle. And also other dynamic libraries. Then lower than that, we have the heap. Heap goes up. And at the very beginning of the address space, we have, well, when I say very beginning, I'm not talking about the very first page. The very first page usually is always unaccessible. We cannot access that because in C, we define the 0 is not accessible, right? C is the non-pointer you cannot access. You cannot dereference that. So that's why usually we reserve the very first several, what is that called? Pages, right? Then after that, after the very first pages, we can have several segments for the text, for the data, for the uninitialized global variables. So this is a view, the static view of the very old process. Go ahead. I tried, but it's not working. Is it better? Yeah. Okay. Okay. So, so for the traditional static program, when a process is created, the kernel will bring the code section .text from the executable file to a fixed location in the virtual address space. And accordingly, some data, BSS, they will be in some fixed location. Even the stack usually starts at a fixed location. So all those locations, they are fixed. That is the traditional. That is a traditional address space. But however, actually the BSS, they don't need to copy from the executable to the memory, because BSS is for uninitialized data. So it doesn't really have an initialized value. So its value doesn't really matter. What the loader or the kernel needs to do is to reserve space for that and initialize that to 0. Actually in C, the standard is to initialize this section BSS to 0. So if we use a dynamic linked program. So this one is a static program. So everything is statically linked together. There's no like dynamic library. Then for a traditional dynamically linked program, things will be a little bit different. So the kernel will first load the runtime linker. Usually it's in Linux, it's called the ld.so. That's a loader program. So this is still a user space program. This is loaded to the user space. And this loader program will load the executable into a fixed location. So everything is still fixed, but it can map different dynamic libraries into the address space. And those dynamic libraries, most cases, they are still mapped to a fixed address. Well, that's a fixed address in the virtual address space. So there is only one, for example, there are two processes running on the same program. Both of them are dynamically linked with libc. So physically, there is only one copy of the C library, the libc, in your main memory. But each of those two programs, they have their own address space, right? They have their own 4 GB address space in 32-bit version. And in that address space, both of them, each of them map the libc at some location in their address space. So they do not have to be mapped in the same address for two different processes. But eventually, they are mapping to the same physical libc copy, which is in the physical memory. So this is the architecture we have been using for a very, very long time before ASLR. Now, if we use ASLR, if we use this without PIE, position independent code, what we can do is the kernel will load the user code and data to a fixed location. Because this piece of code, the user code is not PIE, is not position independent. If we load it to other places, it cannot run. Okay. However, the libraries, they have been compiled as PIE. So they can be loaded to different places. So that's why the libc, the runtime linkers, they are loaded into different locations every time you run the same process. And also for two different processes, they have a different location. But the user developed the code and data, they are still at the same location. So if we compare things with PIE, then everything can be randomized. Even the user code can be randomized. So next, we are going to see one example. So this is my first example for ASLR. A very simple program. I'm just printing out where everything is. Left-hand side, well, both of them actually are the program. Okay, so you can see we have three global variables here. K, this one, which section does this one go to? This one goes to data section because it's initialized the global variable, and this one is uninitialized, so it goes to the BSS section. Here we actually have two different things. First, we have a global variable, which is P, and P is initialized, so it goes to data section. Then we have a string here. The string is fixed, it also actually goes to data section. We have a function and two integers together. In that, we have a local variable I, and I was initialized. Then we add A and B together, assign to I. We print out the address of I, which should be on stack, right? Then there's a subtract function, almost the same as the add function. Also, we print out the address of J here. Then also we have another function, compute ABC, we just call subtract and add. That's the compute. Computer doesn't have any local variables. The main function will only print out the address of everything and call this compute. It print out first C library functions, their address. To print out where is printf, where is memory copy, and the distance between printf and memory copy. the address of the system, the distance between printf and system. After that, we print out the addresses of the functions we developed. So the functions in this module, we have the main function here, add function here, the distance, subtract, compute. Then we print out global variables address and uninitialize the global variable address. So we just call the function. Okay. So that is the example. So we're going to run this example on my computer. Actually, I have to return. So the reason I'm running this on my computer instead of our server is right now our server, we disabled the ASLR for the previous challenges. And some of you are still working on the challenges from midterm. So we're not going to enable this until Wednesday night. That's why I'm doing the demo on my laptop, but we already put all the batteries on the server. So you can see here, I have the exact same code here, and I'm going to show you the makefile. So this is my makefile. I'm going to compile. Oh, this is an old version of mine. This is an old version. Let me show you a version on my GitHub. So this is the version of makefile we're using right now for the server version of the code. So we compile the same piece of code to 6 different batteries. The first one is just a 32-bit. We didn't disable. We did disable the stack cookies, but for this task, it doesn't really matter. We didn't disable any other protections. So this is a fully protected version. Then we compile it into 64-bit. Then there is a low PIE static version. So this one we give a flag static, which means if we call any C library function, the C library will not be dynamically linked. Instead, the C library will be injected into the executable. So at runtime, the process will not look for the C library function, the shared C library function. Instead, use its own version of C library function. That's what it is static for. Then we have no PIE. So we're not going to generate position-independent code for our process. Then we also compare a 64-bit version of this. Then there is another version called the no PIE but dynamic. For this version, you can say we only tell the compiler our own code is not PIE. I'm going to call C library code, and the C library code is already PIE, so you can load it anywhere. But for my own code, it's not PIE, so you should not load it anywhere. Okay, so that is our 4 programs, 6 programs. So let's just run those programs. Let's run this program and compare them. Let's do the static one first. So we're going to run the no PIE static one. So if we run this one, you can say we find all the addresses, and we can run this multiple times. Let me run it in this terminal as well. My operating system enables ASLR. My operating system supports that. Okay. So, but if we run this program twice, we just run the program twice. You can say all the addresses, they are the same. They're fixed. No matter how many times you run it, they are fixed because you compile it statically, link to them statically, and you do not ask. Basically, you do not ask for ASLR, even though the system supports that. You can say the printf is always at this address 1CD0, Memory copy is always at this address, 480. The module functions, they are always the same. The main function and function, they're always the same. Even the global variables, always the same address. This is also a global one. Yeah. The only difference is the local variables because the stack are somehow different. Okay. So you can say the stack, those stack addresses, they are not the same. So if we run another version, let's say the version not static, which one is it? Let's just do this one. Okay. So this one, the version is not static. We dynamically link with the C library. If we run this one, you can say the address. First of all, those two versions, their addresses are different. Let's run both terminals. We run this one. Okay. So remember, this one is not static. The C library, we're using the shared C library. So as you can see here, the main function, they have the same address. The C library here, oh, actually the C library here, we do have the same address. Let me check, RTD. Okay, I'm using another tool here, which is RDD, to quickly tell me where does the system load the different libraries. You can see I run this program twice. The first time it loaded the C library to this address. The second time it loaded the C library to this address. Let's run this again. Let's try this program. The printf somehow they are the same, but you can see this address. This is not really the printf address. The printf should be some f address. This looks like a stop here. Okay. So the stop, I think I'm printing out the address of the stop, not the address of the real function. So the stop we do have the same address, but the function should not be. Then those two right now they are the same. Okay, let's run the version, the version fully protected. Yeah, now everything is different. We run this twice. So now you can say, first of all, the printf have a different address. This one is F7DAB. This one is F7D8. Okay. Those are two different addresses. However, the last several bytes are the same. It's kind of like there's a base address, you load the libc, and there's an offset. The offset is actually the same, but the base is different. That's why they have different address. A memory copy also have a different address. Then you can see for two different versions, even though printf memory copy, they're loaded at different locations, the distance between them, they are the same. Printf and memory, the distance between them is always this number. Okay, why is this weird number? This is a negative number, basically. How I calculated this, I use this number to, we subtract this one from this one. So I get FF something, that is just basically a negative number. So you can say they have the same distance, which means the loader, when you are loading C libraries there, the granularity here is not that small. The granularity is probably the whole libc, right? When I load this, I randomize things, but when I load the C library, I will randomize the address space, but I'm loading the whole libc to that address space. I'm not splitting that libc into smaller segments and load each of them into different locations. So at least my system is not doing that. Okay? So obviously there will be research thinking about how do we make the granularity even smaller. And of course, the cost is, it may be slower, it may be more difficult for the compiler to generate the code, those kind of issues. Then we look at the main function. You can see there are also different address. This one is 5C1280. Here is 64D2AD. But the last 3 bytes are the same. Last 3 bytes are the same. And the same thing, but the distance between them also fixed. This one is not changed. So we are randomizing where we put the whole module, the module you developed, but we're not splitting the modules into smaller segments and randomize all of them. We're not doing that. Global variables, also different address. So remember, this is the same piece of program. We're just running it twice, and you can see all the addresses are different. So if we do we use nm to check this program, then we can get all of its symbols. So you can see the symbols, the address they have here, start with zeros, right? That doesn't look like a valid runtime address. But if we go to the static version of this, we do name on the static version. First of all, you can see the static version has much more symbols. That's because we put the whole libc inside this executable. And well, we're not going to go to the beginning. Let's show those addresses. Those addresses look like real runtime addresses. Start with 08. We know that's where the code is. And this one, it's for all 4 zeros. That is the very first several pages. Those are not really valuable, valid pages. So those are actually just offset. But those addresses, those are actual virtual address. The loader will load those things too. And if you compare, if we compare the size of those programs, you can say, so you can say this one is statically compiled linked with the C library. That's why it's big. It's 700K. That's because the whole C library is in this binary. And this dynamically linked one is only 16K. It only include the loader, include your code, some standard C library functions. That's it. So you can see there's a huge difference in size. Okay, so now we say how this PIE works. Well, we're going to see one more example to figure out how this PIE works. Let me see. Let's do a disassemble of the program. So on left hand side, we do the original static one. Now we're looking for what? We're looking for this one. This is too big, so let's do head after main. Let's do this. Should be A, right? Print. Okay, just do it. Okay. Okay, so what I'm trying to do is to grep So we're looking for the main function. Then we do a head, maybe 29. Let's do this. So we can say this is a main function. Oh, this is not really main. This is a main. Oh, I was doing a graph set. Okay. What should I do? What is the command I should use here to? So I'm not supposed to use head. I saw head and after. Sorry about that. Forgot how to use the command there. It should be grep, right? Grep may have after. Operating file. Oh yeah, here. So grep should have after. Okay. So we should do a grep. Grep this after. Okay. So this should work. So this is the static version of the program, and you can see the main function looks like this. If we go to the static version, the dynamic version, we do the same thing. J dot. Okay, so we have two main functions in those two terminals. And you can see the major difference here is actually this line of code. This call x86 get pc thunk.bx. So this is a piece of code. This is a function, say library function, for the program to make the program PIE, to make the program independent, precision independent. So at runtime, this function will get some kind of a base address. Then you can say, then you get the base address into bx. That's why you can see many versions of this function. There is a bx version, there is an ax version also for other registers. So basically put the base address into those registers. Here we put the base address into bx. Then we add a pre-compiled value to bx. So bx has a base address and we already know the offset. Then after this, the EBX will have the runtime address for something we're going to use. And we save the runtime address somewhere. But if you look at the static version, we don't have those things. Everything we know exactly their location. For example, there is a put. Here we also have a put, right? The put is going to print out what's that? Maybe the very first thing we print out is just a 1 line there. To print out that, we need to know, maybe we'll print out a string something. We need to know the address of that string. For the static version, the address of the string is here. It's a fixed 80E6044. That's the address of it. But for the static version, the dynamic version, we don't know where that is. Only at runtime we have to figure out where it is. That's why you can say here that's a put core, and the address is in EAX, and the value inside EAX is dynamically calculated first from this function. Somehow get the base, then do a lot of calculation, we get the address of that string, then we print out. So everything is randomized in this version. Does that make sense? Cool. Okay, let's move forward. So some papers, they reported that the overhead for PIE is around 3% in the 32-bit machine, because the 32-bit x86 they do not support using directly address things using EIP. That's why we have to use that x86, get PC some functions. There are a lot of versions of that function. However, for 64-bit, the architecture has some kind of optimization, so they can use direct RIP relative to addressing. So if you keep the resources you want at the same offset of your code, you do not have to fix its location. You can just use a current code location, which is in RIP plus some fixed offset. It's not a perfect solution, but it's better than without that address space organization. And that approach, the overhead is around 1%. So usually young normal Ubuntu machines, we can use those commands to disable or enable ASLR. Obviously, you need a root privilege to do that. So next, same as how we bypassed stack cookies, we will talk about how we can bypass ASLR. Because this is not a perfect solution. You can say the idea is good, but in all security defensive solutions, there is an idea, then there is an implementation. Even though the idea could be perfect, the implementation may have a lot of issues. The implementation, because there is a trade-off between performance and security, and you can always find a vulnerability somewhere. There are several types of vulnerabilities we can find and utilize to bypass ASLR. The first one is address leakage. So even though there is ASLR, let's say some C library functions loaded at a random location, but maybe the source code you developed has a bug, somehow it leaks the address of other functions. So it tells us where those functions are. Then relative addressing, like we saw the 64-bit version before. We are in 64-bit, we're using RIP as the relative addressing base. So it's not a very fine-grained approach. So we can also use that to bypass that. Also, there are side channels we can use, but we will only talk about side channels in the last 2 weeks of this semester. Next, let's say a much more concrete example, and we're going to hack this program. This is a very simple stack-based buffer overflow. You should be very familiar with this so far. The only difference is this one we're going to protect it with ASLR, then we're going to hack it. Okay. We have our main function, the main function called valfoo. Valfoo prints out the valfoo's address for us. After that, well, this line of code doesn't really take any space on the stack, right? This is just a print out. Then there is a local variable buffer, say level 8 bytes. Then there is a get. Well, this is a vulnerable function. We can input as many bytes as we want. So obviously our goal here is to overwrite the return address of Vulnerable and get into print secret. That's our goal. The problem here is we're going to say this. So let's just do the 32-bit version. Say this is a 32-bit version of the code. We run it. You can say Vulnerable is at this address. We run it again. You can say Vulnerable is at a different address. Here we have 5.8. Here we have 5D. Okay, different address. We didn't print out where printf, not printf. The print secret is, but we're going to jump there. So what is the idea here? How do we find out where that print secret is? We don't have to go that far. Much easier than that. Okay, well, we have the binary, right? Do we have to guess? Yeah. In this case, not really GDB. What we can use is we just do object done or NM. Then what we can get from that? We're getting the offset, right? We're getting the offset. However, the beginning several bytes, this should be the same as this Vulnerable, right? Even though the Vulnerable it changes, but it should be the same. So how do we do this? This one take input from std in, which means we need to type something there. Okay, let's do JDoc. So this is Vulnerable. We can say where's the vulnerability. The vulnerability is here. This read. So here we have the printf. That's print out the address of Vulnerable. Then after that we have this read, and this read is where the overflow happens. The read has several. Read has 3 parameters, right? Let's do a main read here. Read has 3 parameters. The first one is the file descriptor. Here we're reading from std in. We're actually in Seccomp level. In our program, we're using the C library function gets. But when you compare, you eventually compare to the read function. And the read function use first the file descriptor 0, which is std in. Then it's a buffer's address, is a number, how many bytes to read. So what we can say here is we first push, well, we push the 0 last, and this one is std in. Then we push the EAX, and this is the second argument, the buffer. So the buffer is at EBP minus 10 hex. Okay. Then higher than that, this is the number of bytes we're reading from that. So now we know that we are from the beginning of buffer to the saved EBP, we have 16 bytes, right? Because hex in 10, so that's 16 bytes. After that, 4 bytes of garbage for saved EBP. Then we have that 4 bytes of address. Do we have to overwrite? We do an M here for we are looking for print secret and also main. Okay. Come, look at those offset. One is 12.8 say, another one is 12.0D. Only one byte difference. So go back to here. What happens is this vol foo is called by main function, right? So when the vol foo returns, it's supposed to return to somewhere in the main function. It's supposed to return to somewhere, maybe, so it will return to 12 something or at most 13 something because the main function is small anyway. Does that make sense? Okay. So which means at runtime, this address will be added, this offset will be added to another base address, which we don't know the base address, but the base address will mainly be those first 2 bytes and maybe part of this 3rd byte. I'm not sure how many bits here. So we probably can get lucky by just overwrite the last byte. Because part of the return address in the main 4 bytes, all 4 bytes will be pushed onto the stack of vol, right? And the lower, the higher bytes were at a higher location. The least significant bytes will be at a lower address, and we are writing from the lower address. So probably we just overwrite OD there, 0D there, and do not touch the other 3 bytes. We can get to print secret. That's possible. It's also possible that we maybe need to write 1 more byte, but we can try that. Okay. So then we go back to here. Let's go down here. We go here. So what we're trying to do, Python print. How many bytes of garbage again? 20 bytes. Then 1 byte to 0D. That's maybe it. Let's see if it works. Nope, this one didn't work. That's probably because here. Yeah. Because 16 bytes from buffer to save the EVP, then 4 bytes of save the EVP. Together, 20 bytes. Okay, I think so here we can say, let me run this again. 2. I think we should change this one. But we cannot overwrite. Bytes, 4 bytes, right there. I think we may get lucky. We keep doing this. Do you understand why it's not working? I think it's not working because of this. Because this one is at the beginning of 12 OD, right? And this main is at 12 HC. So where we return to is probably 13 something. That's why if we override 1 byte, we're actually returning to 12 something, not the 13 something. We're 200 bytes off. But I'm not sure if we can override 2 bytes here because we don't know what is the 2nd byte. So looks like the 2nd byte we have to guess. That will be will, because I don't think it will always be 13. There is a base main. Let's try this. So it may not work. Oh, hold on. I did it wrong. Should be this one. Okay, it's still not working. We can confirm that by debug this. Let's debug this. Let's set up breakpoint at Volfu. Then we just run this. So let's say where the main is. So main is at this address 28C. And where is print secret? So print secret is, oh, in this case, they are. So where are we returning? The question is in Volfu, where do we return to? So where do we return to right now? We already pushed out the stack. So actually we only need to examine stack. ESP. Hold on. We are here. So we should get 4 bytes. Okay, so we are actually returning to this address 62A5, and print secret is 620D. Okay, so this one should work. How about this one? This one should work. So what's the problem we have here? Is gets the problem? I use the wrong function here. Let's see. Oops. So gets will read a line. Okay, I think gets has a problem here. Okay, I should update this example because gets will attach maybe a 0A, which is underlined to what you put there. So it's basically we're not, even though we are giving 2 bytes, giving only 1 byte, 0D there, it's actually writing 0D OA there. I think that would be the problem. Let's double check this. We can't check this by, we run this again. This time we are redirecting from this some say print A times 20 plus 0D. Okay, that looks correct. Hold on. Do this. Okay. Now we are in Volfu. Volfu is at this address. Let's print out where what do we have on stack. Okay, this is what we have on stack. We're going to overwrite this to 620D. That's our plan. So should we go here? Going to print on our waiting board. Okay, so read is overflow. So we are going to for this. Now we should have already overwrite that. And let's check what we overwrite. We exam 4 bytes from exam 4 bytes from EBP plus right? That's our return address. Okay, see, that's a problem. Because the gets, we actually successfully override the last byte to 0B, but the gets attached to 0A. That's why it's not working. But if you get the idea here, so if I change the whole function to another one, to operator, then it will work. But if you get the idea, we don't have to fully override the 4 bytes. We just the first several bytes, they are from the base address. It's dynamically calculated. We don't even touch them. We can get what we want. I will update this challenge. So on Wednesday homework, you will be able to crack this one. Okay, so that is basically showing it is still possible to bypass ASLR. If you want to know more about ASLR, I would suggest you to read this paper published in NDSS 2016. NDSS, which is NDSS is another top value for system researchers. So one of the limitations of the deployed ASLR systems we are using right now is it's one-time randomization per process randomization, and it happens before the program is loaded. This is very similar to the stack cookie, or the one-time randomized. So how to, well, like you mentioned, if we fork this, they will have the same one. So this paper is talking about how do we randomize things even if a program when it is forked. So this has applications for web servers, especially because web servers usually fork a lot of programs. So basically, this paper is talk about every time there's a system call for fork, then they will reanalyze the program and re-randomize everything. And you can see this is like 6 years ago. You can even push this further. When a program is running, it's not even calling any system call for fork. What if we re-randomize it, right? So, and also how can we push this into IoT devices, those very low-end devices with smaller address space, without MMU, how do we randomize those things? Actually, my team looked into that last year. We almost started a project. When we have a rough idea how we want to do, a rough design, then we find out a paper was published this year actually. Then we start the project with a very high quality paper. So someone already implemented this on very low-end devices. Okay, so we still have another topic to talk about today. This is the last defense we are going to cover here. This one is called the Secure Computing Module, or Seccomp. So this is a kernel system call mechanism. This is basically a firewall for system calls. So far, we have discussed several defenses to stop stack-based buffer overflow. We have talked about making the stack. If you inject the shellcode there, then you inject the shellcode in the stack. Then we make the stack not executable. So even if you can inject, you cannot execute any instruction there. Then people say, I do not inject, I just jump to existing function calls or libc. Then the libc will make some system calls, right? For example, we make the libc function system eventually makes a system call exe, cd, something like that to create a new process. So how about we just stop this program from issuing those system calls? We do not allow this program. We have an application. We do not allow this application to make system calls like exe, cd, like open. What if we define that? So obviously this is a kernel thing. So we confine dangerous operations from an application. We have a whitelist or a blacklist to say what are system calls you can make. And syscall is such a feature. It's already embedded into our Linux systems. I'm not sure from which version we have this, but basically this is a module that allows developers to define some rules, and these rules allow certain system calls or disallow system calls. Oh, I actually have a history page. So this was first designed in 2005 and merged into Linux kernel also in 2005. Then Android also started using this in 2017 using Seccomp BPF. Okay, so Android actually using BPF to do this. So BPF is another system feature introduced by Linux. It's called BPF, short for Berkeley Package Filter, I believe. So it came out from UC Berkeley. It's a small virtual machine idea to run userland applications in the kernel. Originally, it was designed for the network modules, so you can analyze network packets. But then we realized this can do a lot of things, not limited to network packets. So if you are interested, you can search for its BPF. Going back to Seccomp, so this is an example code. We have a if define my sandbox, then this is a very simple program. This program does one thing. It will execute cat, then you will cat a secret file. That's it. So this one eventually execl eventually will map to a system called execl, create another process, and that process is just the cat program under your bin folder. Then what does the program do is to cat the secret file. That's it. So if we, I actually put this in the server. So if we run this program in the server, the program will just obviously I changed the secret to flat, right? On the server, the secret is a flat file. It will just print all of the flat file for us, the content. But if we define this my sandbox, then we are going to run this 4-line code. And this 4-line code will set up the Seccomp firewall for us for this program. Okay. So the first is we define a context to use this firewall. Then we initialize it, and the default operation here is allow. So we are going to allow all system calls after this one. Then we are going to add another rule. The rule here is if there is a execve system call, we are going to kill this program. Okay, so simple as that. Then we load this context, which means we enable this rule. So if we compile this, we will first stop using the system call execve, but we can use all other system calls. Then we are going to do this one trying to issue that system call, and the operating system will stop this program. So we can show this demo using this one. This is the other program here. So if we run this, we will say ban system call. The Linux operating system stops this program. Okay. So this is a firewall approach. However, you can see this program is not perfect. This can be also bypassed. What if there's a, let's say there is a stack-based buffer overflow here? Then how do you bypass this? your goal here is to create a new process. How do you bypass this? What? What do you say? But if you, okay, let's say we want to create a specific new process, let's say can't. Your fork is not going to create can't, right? So how do you create a can't process? Well, no, because if say, for example, you return to system eventually also calls this system call, and which is not allowed. So this piece of code will disable the system call exe3e. Why don't you just develop a shellcode to enable the system call exe3e? You can do that because there is no one stopping you from doing that, right? So you can develop a shellcode. That shellcode will basically do the same thing here. Instead of create a new rule or remove the rule or kill this exe3e. Then after that, you jump here or your shellcode can have a can to keep doing the malicious things you want to do. Make sense? Okay. The problem here is the code you are injecting still has a privilege to do that. Okay, that's what I have for today. Wednesday, we talk about shellcode. Any questions? It can be anywhere. So basically, you can say this node is basically enable this rule, and then anywhere you can load it again. Then you have a new rules. Yeah. Yeah.
So sometimes we call it challenge.
Yeah.
So this, I have a quick question.
Yeah, I have a quick question. So here we are distributing the system call. So in a complex application, the application sometimes needs system call. So how we want to differentiate between whether it's a hacking based system call or just a normal system call that the application needs to complete it.
Well, the system call, first of all, they're all normal, right?
Yeah.
It can all be denied, right? So here is just a firewall. Same thing as the other firewall. How do you know this package is malicious or not?
Okay.
Right? How do you know the system call is malicious or not? It's hard to tell. So here is like, for example, my program is, let's say, a video game program. Why would my video, and I'm the developer of the video game, I know what kind of system code is issued.
Yeah.
Right? Why do we issue some system code that I was not design? I didn't design. It means some malicious code will inject it. It should be disallowed anyway, right?
Okay.
Yeah.
Got it. Thank you.
So this is
Ah, I see.
select this, like this. So this is the address.
Yeah, but it may not be the exact address as you run it here, you know, it will be a little bit different.
So I subtract the 6 from 3.
No, don't. It's not about that 6. I'm not talking about that 6. It could be a little bit different. Well, okay, let's see what you have here. So what you have here is, looks like you have some syntax. How many? Let's see. Because here is a command log one. You are actually doing a command. Oh, okay. Yeah, you have some syntax error. Good. Okay, first of all, we don't need the dollars down here. We don't need the dollar because we're running this program. We're not giving it a command line argument or anything. Okay. Okay. So, what is the program again? What I'm doing? We're looking at. We should do evolve to somewhere there. Okay, the evolve is small. Okay, that's a get here. Then EBP minus 6. EBP minus 6 and gets what was oops. When this happens, what should I do? Okay, well, still there. So why do you decide 10 there? Okay, 10. Then that is oh, okay. I think here first you need another 4 bytes of garbage. You need 4 bytes of garbage here. Then here, hey, this one. We should swap those two. This part should be the address of the function. So that's one.
Oh.
Let's do this, right? Because after this should be the address of the function, right?
Yeah.
Not that, so let's try. 60, 1D, 49, 80. That looks a little bit weird. I think the address looks a little bit weird, but let's try that. Let's see. This one, yeah. DE. Need this part. Okay, I think this address is something wrong.
But I
See? Look at this address. This should start with 08. This is only 7 digits. Look at the address. This is only 7 digits. What's the address you're giving me?
there's something 0.
No. There is another 0. No. Let's see. What you have here is what you have here is 0, 8, 0, 8, 0, 4, 9, 2, F6, right? This is a lot of bytes. 5. Here, there actually another 0. Like that. So why you have, so it should be not. So it should be not. Oh, that's why here it should be 0, 8, not 8, 0. Okay. This may be correct. Let's see. No, where is that function thing? So 91D6. Let's see why you get it wrong. How did you get this address?
I read that principle.
That's why. That's weird. That's not the correct address. You can see here. That's not the correct address. The correct address is 91D6. I don't know where you get the address. Should be this address. Yeah. 49. No, should be 04 91 D6. Oh yeah, that's because you have that one byte off. Yeah. Yeah, that makes sense. Because you put the 9 here. So the correct address is this. That's the correct address. Yeah, that's the correct address. When you get here, you are getting close. And say, now we're trying to open a file, but then this address is not correct. Okay, then you can take a look. Where is that address? Look, I cannot open the file s pipe blah blah blah. Look here. Yeah, somewhere here. See? Your pointer is pointing to here. You just need to move that smaller to make it point to the thing. Yeah.
Size of chat 6 volt.
Well, no. You are here. You're not. You're here. So see, you are you are either here or here. We don't know. Okay. So you need to subtract the whole part. Maybe. Well, let's try 10, right? We can try 10. So let's see. We have BF. Let's say B0. We're subtracting 15 here. We can say now we're at SE. We're here. See? SE user. We need to abstract a little bit more. You'll get it, right? For example, let's try CD. We're getting closer, but not yet. CD, we're here. Okay. Oh, we should not be B CD. We would B0, so we should be AD. Okay. AD we're already here. Okay. Even closer. We're here, close. So we're going to 4 more, 5 more, kind of like 9 more from here. Kind of like D is 1. D is 14. 14 minus 9, 5. Something like that. Something like that. Oh, we're here. Okay. Where are we? Oh, yeah. Maybe 4. Yeah, 4. Yeah.
What do it by yourself?